development of an IoT slope monitoring system, and a case history of Kratu Patong road landslide in Phuket, Thailand. Our speaker will be Dr. Apiniti Jyoti Sankasa, and he is with Kasartsart University. So I'd like to invite him to the stage.
Thank you very much, Mr. Chairman, for our introduction. So today, the topic of my talk will be on the experience on the use of the IoT slope monitoring system during the emergency case when they have the landslide that hit Phuket Patong Road in Phuket. So I'd like to acknowledge my co-author, Mr. Wachirat Prapatsorn, Mr. Isranu Chanthorn, Dr. Akapat Sawang Suriya, and Dr. Paranik Chitarikun. So the outline of my talks, I will introduce the role of the instrumentation and the IoT technology, the sensors that we use, and the online slope monitoring platform that we have developed at SEAGC-AGSSEA, and also touch upon the various warning criteria that we introduce, and also we will elaborate that with the experience in Patong landslides, with the warning events, and so on, and then afterwards we'll conclude. So just to give you some recap on the instrumentation in geotechnics, we know that instrumentation play a pivotal role in geotechnical engineering, so this actually allows us to make informed decisions during the design, construction, and maintenance of the earth structure. And this approach is often called learn as you go, or observational method. It was coined by the father of soil mechanics himself, Carl Suzuki, also proposed by Ralph Peck. And this essentially involves making the adjustment during the process of construction and design based on the instrumentation data, and also with ongoing geotechnical analysis that can be done during construction when it's necessary. So when we put the instruments, we need to have a clear objectives of the types and locations, and those objectives can be safety through early warning system, or using the observational method, as I already discussed, for construction control, and also for legal protection and managing public relation, and for us, for university, for R&D purpose, of course. However, the true value of the instrumentation is dependent on the timely display. So especially during the emergency time, we need to be able to communicate those results in a timely manner. We call Internet of Things, enable us to be able to monitor these various geotechnical parameters in situ, which can be accessed online via web-based application in a real-time fashion. And it's becoming more and more economical feasible. So we have smart cities, smart home, like smartwatch to look after our health and so on. So why not have a smart monitoring for slopes? So this is the screen capture of the slope monitoring platform that developed by Department of Highways together with SEAGC-AGSSEA University. And for the particular IoT slope monitoring system developed by our laboratory called Geotechnical Innovation Laboratory at SEAGC-AGSSEA University. So we call this platform GILD platform. And there are tensiometers, so with the high entry ceramic frost stone, and piezometers, soil moisture sensor, tilt meters, in-place inclinometers, and rain gauge, tipping bucket rain gauge. All these sensors are connected to an Arduino-based microcontroller and communicate through what we call the narrowband or NB-IoT protocol. And let's have a look at the online slope monitoring platform. So this platform allows for automatic conversion of the sensor unit to the desired engineering unit. For example, from millivolts, volts, 2 kilopascal in percentage, just using some simple linear equations. But on top of that, we also tailor our platform to be able to calculate all the geotechnical parameters. For example, we can input the infinite slope model to be able to calculate the real-time factor of safety. Of course, this is only the very starting point, so it's only for the translational infinite slope, but you can also input like a 2D or 3D slope stability analysis result as well. And we also introduce what we call the weighted hazard index, because we have a number of sensors, for example, piezometers, tilting, or the movements, or the rain gauge. So we want to have a way to combine all those sensor readings and come up with a kind of an overall warning index. So we use a normalization method to calculate the hazard warning index, which means that we need to have like a threshold value, the maximum value for each sensor reading and the minimum, and then we can give the weight for each sensors. And if you ask me how much weight we're gonna give for each sensor, that depends on the locations, on how much reliable or how much we can trust in the each sensor. So we designed this platform to be able to be flexible with calculation of the overall index, which means that we can assign different weighting factor or significant weights and these threshold values for different kind of sensors. And then we need a threshold, as I said, to be able to calculate the a kind of a warning index. So the threshold, for example, for pore water pressure would come from the critical value of pore pressure that results in the factor of safety of 1. So it could be from the slope stability analysis. And we want to relate that pore water pressure to the soil moisture, because to measure the soil moisture is much more simple, because if you want to measure the negative pore pressure, we need a tensiometer and so on. So we also have the soil moisture sensor. So we need the information on the soil water retention curves. And mostly in the critical condition is the saturated soil moisture. And for the critical rainfall envelope, we can base on the past record that pioneered by Professor Varakon, that we use the daily rainfall and 3D antecedent rainfall as a combination. So for example, this is the rain patterns in the Patong landslide in Phuket. So we can draw a line for failure lines that if the rain exceeds about like 200 millimeter, okay, and then it actually enter the critical or the warning zone. And as far as critical slope movement is concerned, of course, we use tiltmeter for shallow depth slope failure and inclinometer for deeper failure types. And it can be categorized by the rate, very slow to rapid. We can use any finite element analysis to estimate the deformation. But I'm gonna show you very soon that for the real emergency case, somehow we not fully rely on that kind of finite element analysis, because everything has to be done very quickly. Okay, now let's move on to the Kratu Patong road landslides, which just happened last year. So if you have ever been to Phuket, there is a very popular tourist beach resort called Patong. And if you remember the road that go to Patong, it's a very winding road going up the hill and down the hill. And that was actually the main route that go to Patong. And there was a landslide. There was a landslide that was caused by the rain pattern I just talked. So the daily rain was over 150 millimeters. The 3-day antecedents is more than 200 mils, causing a road lane collapse. And because it was a very popular tourist attraction, there were immense pressure to reopen this kind of precarious road lanes, of course, because this is the main route. And a lot of pressure coming from the business sector and so on, and Department of Highways under also pressure on this. So at SEAGC-AGSSEA University, we have already the ready-made the IoT monitoring system. So as a voluntary work, we decided to go there and provide them with this monitoring system. So this hopefully will give the data-driven insights for the management of the traffic during the ongoing slope stabilization work. And they're using the berm, constructing the berm at the toe up. So it took quite a while, quite a long time to do. So everything also be done very quickly. So we work along the night as well. And very one nice story that we brought everything, every equipment on the plane from Bangkok to Phuket, except one thing, the geotextile to cover the piezometer. So we have to, drive around Phuket Island, and from this shop, they said, no, the shop is closed. Go back next day. They said, no, but we want this device for the landslide. And then after the shopkeeper knew that, he drove all the way to give us this for free, the geotextile. So we were very impressed on that. And on the next day, we managed to finish all this instrumentation, putting the piezometer and so on, flying the drone. So the field investigation found we have the 6-meter depth to bedrock and about 1.5 meter groundwater table. And this is the location of the piezometers, tensiometers. Actually, we wanted to install a sensor on the failed slopes, but because of the safety, so we could only install on the back upper side of the road. And then with the model that we created from the drone survey, we draw the profiles and then perform a very simple slope stability calculations. And we incorporate the portal pressure that we got from the piezometer and tensiometers with some observation of the spring lines to construct this groundwater phreatic surface and so on. And then we calculate the factor of safety variation with portal pressure. Because we want to get the threshold portal pressure that we're gonna use to provide a warning, because everybody is waiting for us that after we install the instruments, what is coming out of it, okay? They keep going online to the platform to have a look. So we did a very quick, simple sensitivity analysis to see the influence of the surcharge, okay, and the influence of the buttress construction. So you would be able to imagine that if we increase the surcharge, the critical threshold portal pressure would decrease. And if we speed up the construction of the buttress, the threshold portal pressure would increase. So, and we provide a daily reporting to the local authority to help them manage the traffic. Sometimes late at night, this platform is all automatic, but we need some human interference. So sometimes at night, at midnight, they call me up to ask me what happened. So the warning events, there are some interesting warning events that I like to talk, because I said there were a lot of pressure to reopen the road, this road lane. And they only opened it for motorcycles only. But then a lot of pressure mounted, and then they opened it for regular cars, vehicles. And that actually started to show some induced increased pore pressure due to the traffic. And after maybe a day or two, there were a sign of the movement from the tilting at the surface. So 2 out of 3 tiltmeters exhibit similar response. So I, along with Dr. Boranik from DOH, we were discussing, shall we, rely on the finite element analysis to back calculate? But I think we cannot really fully trust the finite element either. So I think we just have to be conservative. And there is, enough evidence for us to see that when we open for the heavy cars to go on the traffic lanes, there was some sign of the change in the pore pressure and movements. So we give the suggestion to the local authority to reverse their decision to reopen the road. And they trusted us. So, and then they not only be able to reverse the decision, but they've got this evidence to increase the public confidence, that their decision is based on the scientific evidence, not just merely some concern. So after the heavy traffic control, so no more heavy traffic allowed, altimeter indicate no further movement. So we were quite relieved that we didn't give a kind of false alarm or false warning. And then the focus is then more turned to accelerating the berm construction for the stabilization work. So now the road has been fully restored, the lane is fully restored, stabilization work is completed. So I hope that this will demonstrate the capability of the IoT technology, that we can give us some real-time warning, and we can use it to show in a communicable index to the public, especially in the case that we got a lot of pressure to reopen the remaining lane, like in this case. So enhancing the public confidence in the slope safety during and after stabilization. So with that, I would like to thank you very much for your kind attention. Thank you.
Okay, thank you very much. We'd like now to open the floor for any questions that you may have. Questions? I see one there at the back. Yes, please.
At first, thank you very much for your presentation. I would like to have you to explain more about how to decide where is the area that you would like to install the instrument for monitoring.
Yeah, it's a very good question. I think as a geotechnical engineers, we have to face with this question all the times. So install as many as possible would be like the first response, as long as the budget allows. And then the critical area would be like of course, the failure zone, my understanding. But of course, sometimes the reality doesn't allow you to do that, like for this case. But I think you have to combine it with some geotechnical analysis, but don't fully trust it. I never fully trust it. I have to go look to the field, go to the site, and then see really the mechanisms, the cracks, and so on. I think the analysis like this, it gives you some ideas, okay? But always need to go to the site to judge for yourself the critical location, I think, to install the sensor near the failure surface.
Thank you very much.
I think we should end there, and let's proceed to the next paper, but a round of applause for our speaker. The next paper is entitled Evaluation of the Impact of Expansive Clay Heaving on Seepage and Stability of an Earth Dam. And this will be presented by Professor Jeff Chow of AIT, who's also the department head of the Civil and Infrastructure Engineering.
Good afternoon, everyone. This is my title of my presentation, Evaluation of the Impact of Expansive Soil Heaving on Seepage and the Stability of an Earth Dam. This was done by one of my master students' research, and his name is Fahim Shai, and he is studying in Japan for his PhD degree. Therefore, he's not coming, so I am doing the presentation for him. And then Professor Sudisak is the co-author of this paper. So this slide shows the typical, let me show the typical, where's the, can I get the laser pointer? Oh, okay. Thank you. All right, thank you. So let me go back. So this slide shows the typical earth dam cross-section that is commonly done in engineering practice. So in the center of the dam, we often have this clay core to reduce the hydraulic head, therefore reduce the seepage. And then sometimes it is hard for us to use the on-site materials, especially if the expensive soil is available over there, and that's the only available material you can use. So for that situation, if the expensive soil was used, then it could increase the seepage potential, and then you could reduce the stability of the dam. So the objective of our study was, the first one is to determine how the heaving of expensive soil could change the SEAGC-AGSSEA, the soil water characteristic curve, and also the K function. And also, with those changes, how does that affect the seepage and the stability of the dam? So for our study, we have two major categories of the study. The first one is we did some laboratory testing. And then so we did some index testing, including basic soil property test, and we also measured the swell potential of the soil, and we measured the shear strength of the soil. And then we also did the filter paper test under different conditions. It's commonly the soil will be compacted at minimum of 95% degree of compaction with plus or minus 2% of optimum water content in our geotechnical field. Therefore, in our study, we varied the dry density value, and also we varied the optimum water content value. So with the time limit I have here, I would only show you some of the examples of our results. And then after that, we also did the numerical modeling to analyze with those changes on the properties, especially SWCCs and K functions, how does that change the seepage, and how does that change the stability of the dam? So let me go over the laboratory testing results first. So this table shows you the basic index properties of the soil. And then, so it was classified as a CH material. If we use the liquid limit and the plastic or PI value to classify the expansion potential, and then the material was classified as a high swell potential material. So on this slide over here on the right, we use this GDS automatic automaton machine to measure the constant variance swelling pressure. By the way, this machine was donated by Professor John Nelson, so he's sitting over there, so thank you, Professor Nelson. And then, so when we received the material from our side in Thailand, we did different variations of the water content and density. So this slide shows you if the soil was compacted at the maximum dry density with optimum water content, then we have about 107 kilopascals of the swelling pressure. And then if the soil was compacted to, let's say, the same maximum dry density with 2% of the optimal water content, then the swelling pressure was reduced by 4.6%. And then if you do 95% of the maximum dry density and then compacted at the 2% wet of the optimum, then the swelling pressure was reduced further to about 20%. With those reduction of the swelling pressure, you can calculate the depth of potential heave. So first of all, the depth of potential heave is defined as the depth at which the overburden pressure or overburden vertical stress is equal to the swelling pressure. So this will be the maximum depth of the active zone, the maximum depth that soil could heave. So for the soils we received from our site, the depth of potential heave will be varies around 6 feet, 6 meters here, and then maybe about near around 4.5 meters. So this figure shows you if you compact the soils at different degrees of compaction, you could have a different depths of potential heave, and then the number could be decreased by 21%. So basically what we are seeing here, it's better to compact the soils at the wet of optimum because we want to have the less soil potential and the less depth of potential heave, so it will have a smaller impact to our stability of the dam. And then we also measure the shear strength using the direct shear test. Here are some examples of the test data. We compare to the non-soil potential case. The friction angle was about 26 degrees. So if we started with the same dry density and then the same water content, and then it becomes the expansive soils, then the friction angle was reduced by about 5% after it swelled. And then the same comparison was done for different water content and density. So for example, if you compact the soil at 95% of maximum dry density, and then at the wet of optimum by 2%, then the friction angle could be reduced by 25%. So this has an opposite effect to the soil potential. On the previous slide, I said, well, we want to get the smaller soil potential. However, when you get a smaller soil potential, you compact it to the wet optimum, then the shear strength is reduced. So that will be something we need to be careful about. We also measure the filter paper. We use the filter paper test to measure the SEAGC. So this is a very standard way people will measure the SEAGC curve using the filter paper test, which includes the filter paper sandwiched in between the soil samples to measure the matrix suction. And then you also measure the total suction on the top of the sample. And this is the end of the setting. Then we put the sample in the container for at least 7 to 14 days until the equilibrium reached. So this is the SEAGC of our sample compacted at different levels of the degree of compaction and also the water content. So, and also we measured the K-set value of the sample, and then we use this equation to estimate the K function. Numerical analysis part. So this slide shows you the configuration of our model. So we set up a dam over here with the clay core in the center. And then again, we varied the clay core properties under different conditions. For example, here on this slide here, we show if non-expansive soil is used, what could be the seepage rate and the stability to our case. And then we say for our site, because our expansive soil maximum depth could heave is only 6 meters. Therefore, we actually did one scenario to consider only the top 6 meters could heave. Then how could that affect the seepage and the stability? And then we also analyzed what if more expensive soils is used, then that depth of potential heave could get deeper. So we analyzed with different depths. It varies from 12 meters, 18 meters, or even the entire depth of the core. If that heaved, how could that affect the seepage rate? How could that affect the stability rate? So this slide shows you the effect of the depth of potential heave or the depth of expansive soil core on the seepage. So from here, this is the seepage versus the depth. It starts from 6 meters. If the soil was expansive up to 6 meters, over here, it doesn't show a big effect. And the reason is because the maximum water level is about 3 meters below the clay core. Therefore, the area that could heave is very small. It could actually affect the seepage. However, as you get deeper and deeper, as the expensive soil is deeper, then, for example, if you use expensive soil for the entire clay core, the seepage could be increased by 130%. Same thing on the stability effect. From here, we can look at the effect of the depth of expensive clay core used on the seepage, on the slope stability. So if we look at the slope stability versus the swirling depths, if you use the expensive soil all the way up to the bottom of the clay core, luckily we only have about 2% decrease on the factor safety value. So my conclusions and recommendations are, well, using expensive soil in clay core could have the significant effect on the seepage rate. The factor safety for our case was reduced by only 2%. However, this is the number in our case, so I don't want to put that as a general number for all the cases. And my recommendation would be we need to actually run analysis. If the swirling movement is a concern, then expensive soil should be compacted at the lower density and at the width of the abdomen. And then if the strength is required, then expensive soil can be compacted at the dry abdomen, but the swirling of the soil could actually have a higher swirl potential too. So that has the opposite effect that we need to consider. If permeability is the main concern, then the expensive soil can be compacted at the width of the abdomen. So that concludes my presentation. Thank you.
Okay, thank you, Professor Chow. So let me open the floor for questions. Yes.
Thank you very much for your kind presentations. And what I like to share is there any alternative if we face with the expensive soil? Could it be that we know exactly what would be the swelling depth, potential swelling depth, or expansive depth? Could I treat the soil with some chemical like a cement or something that it might be I don't know, economically cheaper or not, or it would be something that we don't have to worry about in the future? Could you?
Thank you very much, Professor Woragong. Okay, well, first of all, it depends on your project. Like the project we did here, because we determined the expensive soil could heave only up to 6 meters. And then the water seepage rate was reduced or increased by very small amount. And then the factor safety was reduced by a small amount. Therefore, expensive soil heaving has no effect to the stability of the dam. Therefore, on this case, no, you don't need to do anything. However, if you have if the seepage rate is a concern, and then the depth of potential heave is all the way to the bottom of the core, like the data I showed, your seepage rate could increase by over 100%. Then that could be a concern. So under that situation, you will need to do some treatment to the expensive soils. And commonly, people use lime to treat the expensive soils. And more advanced approach, people use rubber band and other materials. There are some techniques you can use to treat the expensive soils. John and I have a textbook about foundations on expensive soils. We have a chapter talking about treatment of expensive soils. So I'll be happy to show you that. Thank you.
I think my co-chair has a question for you.
Okay,
No one else?
thank you.
So thank you so much, Professor Jeff. It's very interesting presentation. So I just have a quick question to ask you. Actually, did you apply any wetting and drying cycle before you try to measure the swelling pressure and also the SWRC? And what will be the effect to the conclusion? Thank you.
Thank you very much. That's another topic of the PhD study. So no, on this project, no, we did not do it. Expensive soils, after several cycles of wetting and drying, you're correct. The heaving potential reduces. And so there are several studies that has been done about this topic. Therefore, the material properties we measure on this case, it's a fresh, compacted, expensive soils. Therefore, the swelling potential could reduce with time. So, that's another factor can be considered.
Okay, so if I think we only have time for 2 questions. So thank you very much, Professor Chow, for your presentation.
Thank you, everyone.
Myself, Vishnu. Today, my presentation topic is selection of ideal landslide mitigation technique for a region based on case study. So this work is done under the supervision of Dr. T.V. Bharat, sir. This is a brief introduction about myself. I've done my bachelor's in civil engineering from Kerala University in India, and master's I specialized in geotechnical engineering from National Institute of Technology, Silchar. I'm pursuing my PhD in geotechnical engineering at Indian Institute of Technology, Guwahati. My research interests are landslide bioengineering, selection of sustainable landslide mitigation methods, unsaturated flow, and strength behavior. So this is a brief overview of my presentation. I will start my presentation with an introduction to landslides, its mechanism. Then I will introduce to our study area. Then I will explain the site details and site investigations that is done, and the numerical model we have developed, and also the numerical model parameters we have used, and the analysis we have done, and different mitigation methods we have performed, and from that the summary and conclusion we have drawn. So basically when we talk about landslides we can simply define as the movement of a mass of rock or earth or debris down a slope. So there are different factors that can affect landslides. One of the most important factors that trigger landslide is rainfall. There are many rainfall-induced landslides occurring worldwide. There you can see the picture of a rainfall-induced landslide that has happened in northeast part of India. Then coming to the mechanism of landslides. The mechanism of landslide, you need to invoke the principles of unsaturated soil mechanics, because we need to know exactly when soil fails in case of a landslide condition. So we have to bring the 3-phase system into consideration. So when the 3-phase system of a soil is considered, then we have to bring in different constitutive relationships, such as the soil-water characteristic curve, which is a relation between the water content and the negative soil potential, also called the suction, which is developed due to the presence of air-water interface. And in the downside, you can see how a rainfall-induced landslide occurs. You can see when an initially stable slope, when rainfall infiltration happened to an initially stable slope, then as the wetting front increases, then the degree of saturation within the slopes increase. As the degree of saturation within the slope increases, then the suction decreases. So additional strength that is the soil is having due to the presence of this suction decreases, and the factor of safety through the critical slip surface decreases, and the soil fails. So this is a landslide susceptibility map of the world, where you can see India is one of the prominent member which faces the landslide issues. And our study region falls under the northeast part of India, which is one of the hotspot and come under the foothills of Himalayas. And also the study area experienced very large heavy rainfall of more than 3,000 mm per year and comes under the zone 5 of the seismicity map of India. So basically, to approach a problem of landslide, the site visit is most important thing, because every slope stability problem is different. So our site actually consists of different buildings that are constructed on the crest of slopes. And at the present situation, the slope close to the stream is facing issues. The building is facing issues because of the erosion, and also the retaining wall close to the building also have failed. This was the condition when we visited the site. So we have asked for a performance of the site investigation studies. With the borehole data, we came to know that it has a top layer lateritic soil of depth close to 1 meter, and after that there is a weathered soil. And the contour map of the region was also drawn to understand the slope cross-section. So this is a numerical model that is developed from the site investigation studies that is done. So basically the studies have been done on a 2-dimensional analysis, and 3-dimensional model is considered to understand whether the 2-dimensional analysis is giving accurate results. So these are the different parameters that we have used. We have obtained the critical angle of internal friction from using direct shear test. So we ignored the effect of cohesion. And the initial moisture content from the field were obtained from the water content sensors that is present. And other values are assumed accordingly from the literature. We have performed a soil water characteristic curve is developed by performing osmotic technique and also by higher WP4 at the higher suction ranges. So these are the results of the initial condition. When in the present condition, if a critical rainfall occurs in the site, then what happens is like the drainage that is coming, the water that is coming from the upstream of the slope is not diverted, and it creates a seepage additional force to the slope. And also the retaining wall that has already failed is now adding an extra overburden pressure to the crest of the slope. So initially, so when a critical rainfall occurs, then we found that the slope will not be stable at the present condition. So as an immediate solution that can be done in that context, we have asked them to divert the drainage and also remove the loose soil material from the surface. So with that, the slope can be said to be marginally slave according to the analysis. Then some mitigation methods have been tried based upon assumed parameters. So we started with erosion control mats. To bring the effect of erosion control mats, we assumed that part of rainfall is not allowed to go inside the slope. With that, the stability of the slope increased. And we have tried also micropiles that are 300 micropiles of a depth of 5 meters, spaced at 2 meter intervals in and around the building and also at the top of the slope. So this has also improved the factor of safety of the slope to 1.18, which is safe. And apart from that, we tried about mechanically stabilized earth walls, MSE walls. Here we assumed different layer of geotextiles at 2 meter length and a backfill. Backfill has been selected based upon the caudal proficiency, and a compaction density of 19 kilonewton per meter cube was assumed. And with that, under the critical rainfall, it was found the factor of safety was around 1.5. And also a seismic analysis based on zero seismic analysis was conducted based upon the parameters for zone 5 region. And it was found that it was coming around 1.2. A 3-dimensional analysis was also done to verify that. With that, the slope was coming stable. So based upon this analysis, the summary of analysis that has been done, it has found that the slope at the present condition is not stable. So as an immediate solution to the reason, because monsoon seasons approach, so as an immediate solution, we can say that the drainage need to be diverted using drains, and also the loose material need to be removed. And with the time availability, if the monsoon is approaching very fast, then erosion control mats or pinning can be done so that the slope will be stable for the next monsoon time. And then as a long-term measure, which is very safe, is what, according to our analysis, was the MSE walls that can be done according to the availability of the time. And these are the few conclusions that can be drawn from the studies. Basically, drainage is main issue. Water is the enemy for landslides. So driving the water away from the slope is very important. So in this case, the proper drainage system need to be established in this region. And the buildings here have been already constructed long back, and it doesn't have more proper setback distance from the slope. So it is very important that a MSE wall will be a suitable solution, but the feasibility need to be understood. And erosion control mats and underpinning can also be a solution, but these are in the long run, because of the setback distance from the slope is not large, and also the degree of weathering, where we found that as the depth of the topsoil increases, that is the soil weathering increases, it might also decrease the factor of safety of the slope. And also the erosion that has happened in the slope, the part of the building, jet grouting can be performed, so the strength of the building also remains safe. These are my references, and thank you.
Okay, thank you very much, Mr. Vishnu, for your presentation. Let me now open the floor for questions. Any questions? Yes.
Thank you. I saw in the results of your analysis, you have a series of trials wherein the factor of safety is presented, but you have not presented a result where the slope has been modified. Why is that so? You did not modify the slope by reducing the height and also the berm.
Yeah,
Thank you.
Okay. Thank you for the question. So in our stability measures were erosion control mats, and the other one was micropiling, and the other one was MSE walls. So in case of erosion control mats, what we assumed was in the present condition and the present condition of the soil, we have decreased the amount of rainfall. That's only we have done. So they are covering it with erosion control mats, and erosion control mat will be pinned into the soil surface. So to accommodate that, we reduce the water infiltration into the slope, and we see what is the factor of safety change that has came. And into micropiling, in the present condition itself, they are making the building safe by pinning in and around the building, so that the critical surface won't pass beneath the building. Up to 5 meters, the micropiles will be going. So the depth of the soil layer is at present is 1 to 2 meters. So up to 5 meters, we are supposed to have good quality rock, so that support they will get, so the slip surface won't pass through that. The slope is modified in case of MSE walls, where additional backfilling and the width according to the field condition is selected. In this study, we have taken, I think 5 meter width has been taken, that has modified. I hope that has solved your query.
Okay. Any other question? I think we have time for at least one more question. Yes, please.
Further to the question about the stability calculation, for the erosion control mat case, you said that you made some assumption of the reduction in the infiltration. Is it based on some kind of field monitoring, or I don't know?
The assumption in case of erosion control mats, that was basically an arbitrary assumption that we made, because we don't have any, we didn't find that much literature also. It's like a common, I'm performing some field experiments based on erosion control mat also. So I have moisture content sensor reading. So for that correlation only I've taken this. So the studies were not published, so it's basically an assumption we made.
So at least it was based on some field observation that you
field
had made.
Field observation, yes.
Okay. Thank you.
Thank you.
Okay, so thank you very much, and let's now proceed to the next paper. So the next paper is entitled Evaluation of Rock Slope Failure Mechanism for the PHPA-1 Dam in Bhutan. And this will be presented by Richen Liamo. Okay, so can I invite Richen to the stage?
Very good afternoon to you all. Thank you, organizers, for giving me this opportunity. So I'm going to present the paper on evaluation of rock slope failure mechanism for Puna Changshu Hydroelectric Project Authority. It's a dam in Bhutan. So this paper is co-authored by my advisor, Dr. Chow from AIT. This is the overview of my presentation. Coming to the introduction, Punachangchu Hydroelectric Project is one of the mega hydropower projects which is under construction currently in Bhutan. And once it is constructed, it will generate 1,200 megawatt of electricity. So for this, the dam for this project has, like the right side of the dam has encountered several geotechnical problems since the start of the project in 2008. The right bank is uncomfortably overlain by a thick layer of colloviums, and the significant movement of the right bank has occurred in 2013, which was triggered due to daylighting of the shear zone on the right bank. So for this, the project authority has carried out stabilization measures. The first sign of instability of the right bank was observed in 2011, where they have observed deformed ribs and uplift of floors in the grouting gallery on the right bank. Due to the major slide in 2013, the excavation work for this dam site is stopped in July 2013. So this is the photo that I have taken from the left bank. As we can see, the outer yellow dotted boundary shows the major slide that occurred in 2013, and the inner boundary shows the slide that occurred in 2016. And the overburden of this 2016 slide got slate in January 2019, as shown in this one. For this, the project authority has carried out various rigorous geotechnical investigation, like they have drilled various boreholes with aggregate depth of 3.7 kilometers, and both surface and subsurface monitoring has been carried out since January 2015, and the various stabilization measures has been carried out, including grouting, cable anchors, installation of RCC piles, micro piles, and shotcrete. So coming to the methodology of my study, after collection of the data, like related data and reviewing, I tried to identify the causes of the movement and also carried out a kinematic analysis. And then the subsurface profile was generated using RockWalk software. And on this profile, the slope stability analysis was carried out using slide 2018. It was carried out on the slope profile before movement and the cut slope at the time of the movement. So for this, the model was calibrated by back analyzing using slide 2018 on a cut slope at the time of the movement. So the analysis was stability analysis was carried out with the support system, which has been implemented by the project authority, and the adequacy of the stabilization measures was checked. So then I come to the result discussion and some conclusion. So for the result and analysis, from the monitoring data, like they have installed around 14 numbers of inclinometers on the right bank, and most of the inclinometers showed movement beyond the depth of the installation, and inclinometer along dam axis showed the presence of shear plane. So this is one of the inclinometers reading, and as we can see, observe some presence of shear plane at the depth of 35 meters below the surface. There were 37 surface targets installed, including benchmarks and deformation points. So readings of these targets were carried out on daily basis, and then the reading showed continued movement, but it was slowed down after stabilization measures have been carried out. So 8 out of 13 load cells showed reduction in load, and some of the load cells showed constant load, which was installed on the hard rock mass. So for this analysis, I looked into the factors affecting the movement of the slope. Like I tried to check the presence geological conditions and found out that there is a presence of faults, foliation, and discontinuities, mainly the shear zone consisting of crushed rock and clay gouge. So I also observed that the rock mass was highly fractured and weathered, where the Q values ranges from 1 to 1.8, and which falls under poor rock class. So the moment geometry extends from 390 meters to 170 meters height, as observed in February 2017. For this analysis, no groundwater was considered for analysis since the groundwater table was assumed to be far below the slope. And then from the rainfall data, it was not that significant for the rock slope, considering low permeability of the rock mass. So from the kinematic analysis, both planar and wedge failure was not significant from my analysis. It's maybe due to less data and the movement geometry being so large. Since no wedge failure was evident at site, planar failure mode was considered for further analysis of the slope stability analysis. Subsurface profile was generated using rockwork software. It was like 2D, both 2D and 3D cross sections were generated using the boring log data and with the help of instruments like inclinometers installed on the slope. So for the analysis, only 2D model was cross-section along the dam axis was used for my study. So this is the contour map that I have generated from rockwork 2016. And as we can see, the red dots shows the inclinometers that have been installed along the dam right bank of the dam. And then the black dot shows the borehole that they have drilled. So after going through the boring log data, I tried to classify the stratigraphy into 4 regions, as you can see here, collovium, coarsophosphate gneiss, and fracture zone and shear zone. And the depth range is as given here. The shear zone depth ranges from 1.4 to 32.4 meters. So this is the 2D cross-section that I have generated for the analysis along dam axis, where I have input boring log data, inclinometer, and as we can observe from this slope, after the failure, toe bulging was observed at the dam toe. And then for selection of failure mechanism, failure mechanism was a planar failure along persistent discontinuity. Since it satisfied the planar failure criterion, like the upper shear zone got dilated and it like the face slope was greater than the dip of the sliding plane as shown in here. So with this limit equilibrium analysis was carried out. For the model calibration, it was back analyzed, and the sensitivity analysis was also carried out for the shear strength parameters. And generalized Hook and Brown failure criterion was used in conjunction with the rock mass classification for the rock layer. So this is the model that and input data that I have used for the model calibration. So with this, the planar failure mode along the weak layer contains crushed rock with the clay gouge, where only cohesion and phi was considered. And during the slide in 2013, the cohesion was assumed to be 0. It would have, the cohesion would have lost during the movement of the slope. And when the factor of safety was 1, the internal friction angle was 17.5 degrees. from the back analysis. So with the calibrated model, I have used non-circular slip surface was chosen, and then the average width and height of the slip surface was 379 meters by 38 meters. So with this calibrated model, I tried to evaluate the slope stabilization along the dam axis. So as we can see, the factor of safety for each stabilization measures. So with all the three stabilization measures, the factor of safety came out to be 1.1, which is still not within the safe factor of safety for the rock walk excavation. With the seismic loading, with the repeat drawdown condition, the factor of safety reduced drastically. So coming to the conclusion, subsurface profile revealed two different intensities and thickness of shear zone, as I have shown already, and the cross section was generated along the dam axis. The critical slip surface was located in accordance with the monitoring data and subsurface profile. Slope stability analysis was analyzed using the limit equilibrium method for non-circular failure. So for the cut slope profile, before the dilating of the shear zone, the factor of safety was 1.3, which was still not within the safe factor of safety. However, further excavation at the dam pit led to dilating of upper shear zone, which I have shown, which has caused the movement of the right bank. After the slope movement in 2013, project authorities have carried out rigorous stabilization measures. So to evaluate the effectiveness of the stabilization methods, a model was back calibrated and it was analyzed, and at the time of the movement, the internal friction angle of 17.5 degree was back calculated when cohesion was assumed 0 at the time of the movement. Despite the implementation of stabilization measures like grouting, RCC piles, and cable anchor along the dam axis, the factor of safety was improved to 1.1, as I mentioned earlier, which is again not within the factor of safe factor of safety as given by Willie and Ma. And the stabilization measure carried out after 2013 slide were noted to be ineffective during the rapid drawdown condition with the seismic loading. I have already shown that one. So therefore, my recommendation was the slope still needs additional remedial measures, and the remedial could be such as removing of the overburden above elevation 12.6 meters are required. Since various stabilization measures have already been carried out, so I recommended removing of the overburden, which has average depth of 34 meters. So with this, thank you.
Okay, thank you very much also, Ms. Yamo. So I'd like to now open the floor to any questions you may wish to ask. Any questions?
Have any questions? So can I have a quick question, please? So basically, I can see that you try to model the fracture of the lock.
Factor of safety.
Fracture, the lock fracture, right? I can see there is a fracture along your
it's along, this is the, I will show the 3D profile. So this is the one of the cross section. So the red line shows the shear zone, presence of shear zone. So I try to
fracture zone by any discontinuity or?
Yeah, it's fracture zone, you mean?
Yeah.
Fracture zone, I have, how to say, I have the input data for, these are the input data that I have used in my model, each layer has their own like a property. So for the fracture zone, this black one, so I have used generalized Hook and Brown criteria. So I have input that data for the analysis.
Thank you so much.
So thank you. Thank you very much.
Any other questions that you'd like to ask? Setio Muntohar, who is with Universitas Muhammadiyah, Yogyakarta, Indonesia.
Thank you, Mr. Chairman. Very good afternoon, ladies and gentlemen. Today I would like to present a paper is wrote and investigated by my students. Basically, this suppose he will present for these papers, but in last September he studied for PhD in National Cheng Kung University. So I replaced him to present his work. The title of the paper is Mechanism of Rainfall Triggering Slope Failure of Volcanic Soil. Volcanic soil is measured in our area in Yogyakarta because we have the more active volcano in Yogyakarta, they call Mount Merapi. So in the location is Purworejo. Purworejo is Central Java. I'm a professor in Universitas Muhammadiyah in Yogyakarta, and Farid is my research assistant and now a PhD student in National Cheng Kung University. This is the outline of my presentation for today. There is the background, objective, and research location and method, and result discussion and conclusion. So just, this is the background of research. In 2016, there is the, I think there is the big rainfall and in the, during the dry season. Commonly, landslide in Indonesia, especially in our region in Yogyakarta, is occur in during the rainy season, during the November to February. But this is the rare landslide happen in during the dry season in June or July. So I think because of the climate change, and then everything is a change for especially for the landslides. This is the area. Yeah. If we like the big view in the height of about almost on. This is the area, and then when we during this when the landslide, we send also our quadcopter there to make some air view. This is the area. This is the road, and almost in this area is the villages, and also it is villages. So after this landslide, so the government authority asked our research center to establish, to develop what we call the warning zone in that area. Which area is safe for the people and which one is unsafe for the people. So this is, for this one, there is 3 cases we have done for the investigate about the mechanism, but this is, I will present only one case in this conference. This is the area. So when we also, before we do some analysis using the numerical, we also investigate on field investigation. We visit the location, the area. We visit the location. This is the area. So totally, all the area is covered by the fatal volcanic rock. The major rock is andesite breccia and tuff. This is the common in that area. And this area, some researchers, many researchers, they say that this is kind of the debris flow, but the issue is that we need to divine, because debris flow is always initiated by the cellular landslide, and then because the continuous rainfall event, and then there is a debris flow followed by the landslide, the cellular landslide. This is the issue. So the objective of the research, we need to define. Yeah, we need to define. We need to locate in which area the initiation of the landslide. This is the area. This is when we see. This is the crown of the landslide. The depth about 10 meters. Yeah, about 10 to 15 meters in that crown. This is what we saw in the bank, this bank. This is the typical the soil and the soil layers. And then we also investigate in this area. When we visit the area, we found also seepage also occur in this area. This is the andesite rock. So this is the weighted rock. This is weighted volcanic rock. This means that rainwater retained in bedrock. So we can conclude that there is the seepage, between between the rock and the rock, and also this is between andesite weighted rock. This is the area. Okay, let's see. This is the location. So during the June, we get the rainfall record from the nearest rainfall station. So near this area, the total rainfall during a day is about 300, almost 40 millimeters. So it's a very heavy rainfall. And then I remember at that location because after the landslide, because I'm one of the team for the National Disaster Agency. So there's the one house near there. There is one family there, so we cannot save that family because the landslide is very speedy. So about very fast. This way, very fast. So this is one of the important. We need to do some early warning system. Okay. For this purpose, we use the triggers model, and also we also combine with other two-dimensional model. Basically, the purpose, we need to, our research center, try to modify the triggers. We will combine with this, use the runoff modeling, and then we can combine also, we still on developing this one. We combine, because triggers model is can post-spatial analysis, we can combine shallow and also infiltration, but in this, the output of the triggers is one of the runoff. But many research study about using triggers, but the research did not use the runoff to analyze like the debris. So in this future, we already discussed with the USGS. So maybe we can modify the equation, the model using our base experience. Okay, this is the model. This is we use some input data. Basically, we could do for this one. The result is spatial modeling. Okay, this is the results. So in this area we see here, we can see here that for this model, this is for initially, there is the slope, the area is relatively safe, but after almost 3 days through this, after 1 day, so there is they initiate here, but small area, but after 4 days, and then 4 days, there is the area with the factor of safety is less than 1, then the number of areas increase. So we can conclude, we can see here that so the landslide is initiated from this area in the top of landslide, in the small area, and then they continue to after the rainfall, because of the continuous rainfall, and then this will be source of the debris, and because of the continuous rainfall, and then this area, this landslide area will be the debris area. We can combine jump to this modeling, right? And then this is the one of the mechanism. So because this area is the initial area for the landslide, and then because of continuous debris, as you see here, this is one of the runoff result of the runoff. Okay, because they are more than runoff, and then this landslide, this one of the source here, and then they go to the toe of the landslide. And when we see in this area, this more more puddle here, water puddle here. This is water because of the rainfall is in this area is high. So estimating the flow with the triggers runoff module can be helpful for two reasons. First, we to get the landslide induced debris flows, and also the second, to use the procedure to debris flow that are formed by runoff and erosion. This is one of the advantages. So To confirm also our result, we conducted 2D modeling. This is the result also, and then also this is the condition of parameter. This is the analysis. If we this is the landslide zone based on our observation, and then we try to make some analysis. This is factor safety. This decrease to the less than 1 during this when the landslides occur in 16 and 19 October. And then for the conclusion, the model saw that the slope instability was initiated by the shallow failure on the tops of slopes of the slope, and then the roundup result from the model is beneficiary to be conducted in conjunction with infiltration and slope stability analysis to determine the flow direction and followed landslide. And the last is spatial modeling using triggers can be conducted in conjunction with 2D dimensional modeling. So this is the end of our presentation, and thank you. All the results can be visited in our website. And also we also developed a spatial early warning, real-time spatial early warning system in Indonesia. Thank you.
Thank you very much. So let's open the floor for questions. Any questions?
For the study, a storm is defined as a rainfall event having at least 30 mm rolling 24-hour rainfall. And in this figure, the blue line is the groundwater level in MPD. The green line is the rolling 24-hour in millimeter following the secondary y-axis. The time is defined, this time is defined as the start of a storm as the rolling 24-hour exceeds 30 mm, while this time is defined as the end of a storm as the rolling rainfall drop below 30 mm. The period in between is defined as the storm period. Then we proceed to step 2. Identifying maximum responses. Within the storm period, the groundwater rises at a rolling window of 4 hours, denoted as delta H 4 hour, are calculated from the first 4-hour rolling window from the start of a storm all the way towards the right to the last 4-hour rolling window until the end of a storm. And among all the delta H 4 hours, the maximum delta H 4 hour is selected and denoted as the maximum 4-hour response of a storm. Then we proceed to the last step, identifying the rainfall intensities that give rise to such response. This is the 4-hour rolling window that gives rise to the maximum delta H 4 hour. And this is the ending time of the rolling window. It is reasonable to assume that only the rainfall happened up to this moment will contribute to the maximum delta H 4 hour. The brown line here shows the rolling 4-hour rainfall in millimeter following the secondary y-axis. The rolling 4-hour rainfall up to this time is examined, and the value of the maximum 4-hour rolling rainfall, denoted as maximum RH 4 hour, at around 90 mm is identified. The above steps give a pair of maximum RH 4 hour and maximum delta H 4 hour for the storm. Repeating the above steps for each storm within the monitoring period from year 2015 to 2021 can establish the rainfall response relationship at BH-MTL 302 at 4 hours. And applying the same methodology with different rolling periods give the relationship between maximum N-hour response of a storm and the maximum rolling N-hour rainfall. And in this study, rainfall response relationship at 4, 12, 24, and 48 hours are analyzed, and the results are shown here. There is a nonlinear increasing trend of groundwater response to rainfall of different intensities and under different durations. This rise is also bound by an upper limit under different rainfall durations. To further investigate the spatial relationship of the groundwater response at different locations, a new parameter groundwater response ratio was introduced in this study. It is a normalized groundwater rise with respect to its physical capacity to rise to the ground level. That is delta H over H at this figure. And An analysis of sufficiently large pool of GRRs of a region would provide insight on spatial relationship of the subsurface flow and other possible factors that affect the groundwater response to rainfall. For the same data point presented at the earlier slide, by dividing its absolute rise in meter at about 2.57 meter by its physical capacity to rise to the ground, that is about 5.5 meter, the GRR of this data point at 4 hours at around 0.5 is derived. And by this, we obtain a pair of maximum R 4 hour and GRR 4 hour for the storm. Repeating the above step for each storm within the monitoring period can establish the rainfall GRR relationship of the borehole at 4, 12, 24, and 48 hours. And it shows similar observations to the rainfall response relationship in terms of meter. The above methodology was applied to other selected standpipes, and similar results are observed. The 12-hour relationship of the three selected standpipes along the two sections at Lumpursham are plotted here as an example. Red data point comes from the monitoring devices at the lower slope, while the blue data points are those at the upper slope. And it is observed that under the same rainfall intensity, the GRR at lower slope is slightly higher. In summary, we have analyzed the rainfall response relationship from some quality long-period groundwater monitoring data at Lumpursham and have the following preliminary observations. There's a nonlinear increasing trend of groundwater response in terms of groundwater rise in meter and GRR to rainfall of different intensities and duration at Lumpursham. The GRR is bound by an upper limit under different rainfall durations. And it is observed that the groundwater response are more sensitive to the short duration rainfalls. And at last, under the same rainfall intensity, the GRR at the lower slope is higher. Thank you for listening.
Okay, thank you very much, Ms. Lee. And I open the floor for any questions that you may wish to ask Ms. Lee.
Thank you very much for your presentation. And the question that I'd like to know is, what is the primary application for the relation between the groundwater and the rainfall intensity? Whether you use it for calculations of stability, or it's just for warning?
At this stage, we target to apply this on the slope stability analysis. Because for the in existing practice, the designer may set the design groundwater level based on the limited groundwater monitoring data by applying different assumptions. And usually, say they may extrapolate the groundwater level. And usually, the design groundwater level is quite high by those assumptions. And so, by back analyzing some site data, we have to have the designer to set a more reasonable design groundwater level. But these are just some preliminary findings and pending for confirmation from more site data.
Okay, in case of the heavy rain, maybe there is a perched water table. That means it's not a very deep water table. In that case, it may create the what we call a shallow landslide. Would it be this application can use for that kind of shallow landslides also?
I think this methodology can also be applied to estimate the perched water table as well. But in our study at this moment, we only analyze the groundwater data of the main groundwater table. But I think we may also collect the existing groundwater monitoring data of the perched water level and apply the same methodology to do some analysis, maybe in some other studies.
And one more short question. Is there any effects from the seasoning or the environmental, like a vegetations or something? A different area may be they have a different environmental, you know. You have to have some correction for that, or you suggest anything to do with that to adjust it?
Actually, the rainfall response relationship are affected by many factors. And what you mentioned, the surface protection, the hard surface, many other factors. And so we are now proposing different monitoring stations to capture more groundwater response. And hopefully by analyzing more data from more sites, we can categorized our observation based on different site settings so as to set different criteria in determining the upper bound for design.
Okay, good. Thank you.
Okay, any other questions? Yes, let's entertain one more question.
Thank you. My first question is, I saw that there is a preliminary findings in your presentation. Preliminary findings in your presentation. Why is it preliminary? My second question is, did you consider the anthropogenic effect? Anthropogenic.
Sorry, I can't capture the word.
Human factor.
Oh.
Anthropogenic effect.
Okay. Let me answer the first question. The reason why it is a preliminary finding is that because, as I say, the rainfall is the groundwater response and rainfall correlation subject to many factors, can be affected by many factors, and we are now only currently we only have some long period data from one particular site at Noi Po Shan. But actually groundwater level can be quite site specific, and it affected by many factors, and different site and different natural hillside can give different response. So we have to collect more data in order to give a more generalized observations and to further proceed to the setting the design guidelines. And so because it pending to be verified by more site data, so I would say it's preliminary. And for your second question, I will interpret the human factor you're asking is maybe the AGMD may be not installed very well in the boreholes, but for those data we have collected from the natural hillside, they are also quality checked by manual dipping. So we have ensured the quality before we make the analysis in our study.
Okay, so I guess that ends this particular session on slope stability. Before we adjourn, there will be just a short announcement.
Yeah, I would like to make an announcement about the presenter in the next session. We are looking for the people for the presentation under the title of Verification of Piezo Drive Cone Data against Standard Penetration and Cone Penetration Test. If you are here, so please try to upload the file in the upload room or contact us.
Yes.
Okay. And I think we can have about 15-minute break and then we will come back here again. Thank you.
Okay, so I'd like to thank our speakers and also your participation in this session. Thank you very much. Sessions in the technical program. This session is on ground investigation, and we will begin by announcing that the first paper entitled Investigation on Acidity Distribution by Peat Soil in South Kalimantan, Indonesia will not be presented. So we will go to our second paper entitled Development of In Situ Direct Shear Test Apparatus and its Application to Dozu Sawa Volcanic Pumice Soil. This paper will be delivered by Mr. Hiromyuki Hashimoto, who is with the Department of Civil Engineering of the University of Tokyo.
Okay, my name is Hiroki Hashimoto of the University of Tokyo. Today I will talk about a method for evaluating the shear strength of high-sensitive volcanic pumice soil using a newly developed in-situ direct shear test apparatus. Here are the contents of my presentation. First, I will introduce the characteristic of the volcanic pumice soil, and then I will explain the apparatus and testing method of the newly developed in-situ direct shear test method. And then I will explain the test results and comparison between laboratory direct shear tests. And finally, I will conclude my presentation. This is the introduction. The volcanic pumice soils are widely distributed in Japan and other South Asian countries and causing serious slope disasters. For example, the 2018 Hokkaido Eastern Ebri earthquake in Japan triggered numerous landslides on the gentle slopes of pumice fault deposits and resulting in dozens of fatalities. And the 2009 Patang earthquake of Sumatra Island, Indonesia, caused a large number of rapid-moving landslides, and hundreds of people were killed. To prevent these serious disasters, it is important to understand the shear behavior of volcanic pumice soils. And volcanic pumice soils generally has extremely loose soil structure composed of fragile porous particles, and with shearing or disturbance, particle breakage occurs and the soil structure collapses and it exhibits large contractancy. And the soil structure of the volcanic pumice soils was easily disturbed during soil sampling, transportation, and trimming. And once the original soil structure is destroyed, it is almost impossible to reproduce it. Therefore, in order to properly evaluate the shear strength of the volcanic pumice soil, it is desirable to conduct tests on site while preserving the original soil structure. As mentioned before, volcanic pumice soils have loose structure with crushable particles, and they are easily disturbed. And furthermore, they are generally distributed in mountainous areas, and sometimes it is very hard to transport testing apparatus or soil samples. To overcome these problems, we developed an in-situ direct shear test apparatus that could evaluate the shear strength of volcanic pumice soils on site with minimum disturbance. And we applied it to the volcanic pumice soil in Japan, and we also conducted laboratory direct shear tests to compare with in-situ direct shear tests. Now I will explain the apparatus of in-situ direct shear test. The components highlighted in red are 3D printed in order to reduce the weight and cost. And the total weight of this apparatus is approximately 5 kilograms, so it can be easily carried by hand and taken to the slope failure site, even deep in mountains. And in this study, up to about 140 kilopascal of normal stress was applied. Next, I will explain the procedure of in-situ direct shear test. First, as shown in the upper left figure, excavate the slope horizontally while preserving the specimen section and cover the specimen with a frame and lid. And next, as shown in the middle figure, set up fixtures, roll cells, jack and displacement transducer, and apply the designated normal stress by means of stone at site or human weight. And finally, as shown in the lower left figure, begin recording data using a microcontroller unit and shear the specimen horizontally by jack operation. The shear plane is generated at the jagged white line in the last figure, And this area is not disturbed before shearing. So we can say that this in-situ direct shear test could be performed with good preservation of the in-situ original soil structure. And then I will explain about the target site of this study. The target site, Dozoso River, is located in Higashi-Kurikuma Mountain of northern Japan, where the 2008 Iwate-Miyagi Nairik earthquake caused a massive slope failure and debris flow that continued for 10 kilometers. Non-welded brown volcanic pumice soils, as shown in the lower right figure, was widely distributed on the ground surface and on the slip cliffs, and thought to be related to this disaster. A particle size of the volcanic pumice soil was mostly between 0.1 to 10 millimeter, and SEM image shows the presence of numerous intra-particle voids in the particle. And the results of single particle crushing tests shows that the volcanic pumice soil had only about 1/10 of the strength of Dog's Bay sand, commonly used crushable soils in literature. And the void ratio of the soil was as high as 1.84. So in summary, the volcanic pumice soil of the Dozoso River had the typical characteristic of volcanic pumice soil. I mean, extremely loose structure composed of highly crushable particles. And here are the results of in-situ direct shear test of Dozoso pumice soil. In this study, 5 cases of experiments were conducted in the range of 3 to 128 kilopascal of normal stress. Shear stress slightly fluctuated at certain intervals due to jack operations, but in most cases, peak shear stresses occurred at about horizontal displacement of 10 millimeter, after which strain softening occurred. This strain softening is thought to be due to shear-induced particle breakage and soil structure breakdown. And for comparison, samples were also taken from the same site and subjected to a laboratory direct shear test. Tests were conducted using intact and reconstituted specimens with normal stresses in the range of 10 to 100 kilopascal. Intact specimens, the left figure, that maintains the original soil structure, reached peak shear strength at a horizontal displacement of 5 to 10 millimeter, followed by strain softening. On the other hand, the reconstituted specimens, regardless of their initial density, reached peak shear strength at later stages and did not reached smaller peak shear strength at later stages and did not undergo strain softening. And these two figures show the comparison of peak and residual shear strength between in-situ and laboratory direct shear tests. The residual shear strength was defined here as the shear stresses at horizontal displacement of 25% of specimen width. I mean 30 millimeter displacement for in-situ test and 20 millimeter for laboratory test. In-situ direct shear tests are orange circles in the figure, and laboratory direct shear tests with intact specimens, light blue squares, showed consistent peak and residual shear strengths, which were higher than those measured in reconstituted disturbed specimens, especially at low normal stresses. So in short, we can say that in-situ direct shear tests could provide a reasonable shear strength evaluations. So this is the conclusion. In this study, we developed an in-situ direct shear test apparatus that could evaluate shear strength on site with minimum disturbance, and applied it to the volcanic pumice soil in Japan, and laboratory direct shear tests were also conducted to compare with the in-situ direct shear tests. And there was a marked difference in the shear behavior of raw disturbed intact in-situ specimens and disturbed reconstituted specimens. And the in-situ direct shear test could provide the consistent results to the laboratory direct shear test with intact specimens. So we can say that newly developed lightweight in-situ direct shear test apparatus is an effective tool for evaluating the shear strength of volcanic pumice soil in the field, even deep in the mountains, while minimizing the disturbance of its sensitive soil structure. That's all for my presentation. Thank you for listening.
Okay, thank you very much. Thank you very much for your presentation, Mr. Hashimoto.
Improvement, wooden piles, and solid or fabric foundations. Accurate determination of the water table is essential for installation of wooden piles, as they need to be buried below the ordinary groundwater table. We hypothesize that the lower edge of the crust layer corresponds to the ordinary groundwater surface, assuming that the crust layer transition from gray to brown is due to oxidation. To address these issues, this study aims to develop a system that contributes to the understanding of the distribution of crust layers and groundwater levels in the Saga lowland. The red dashed line shows the seaward limit of the non-marine clay with a thickness of more than 1 meter, and the natural lower boundary of the Saga lowland, which is the shoreline of the Yayoi period, and the Ariake clay layer is deposited on the seaward side. The thick solid line is the distribution boundary of the marine clay beneath the non-marine clay, and the boundary line is the peak of the coastline during Jomon period, and the upper part of the Hasuike clay layer is deposited on top of the Ariake clay layer in the area surrounded by the red dashed line and thick solid line. The upper part of Hasuike clay formation was deposited especially in the northern part of the Saga plain, and the thickness of the formation depends toward the north. Figure shows the amount of groundwater sampled in the Shiraishi area. The collected groundwater was mainly used for water supply and agriculture. The amount of groundwater extracted for water supply became almost zero after the start of tap water supply under the Western Saga Regional Wide Area Water Supply Improvement Plan in 2001. From 2012, with the completion of the Kasegawa Dam, the amount of groundwater extracted for agricultural use also decreased significantly. A system that contributes to the study of crust layer and groundwater levels distribution was constructed. The system was constructed using Google Earth Pro and QGIS. The thickness of the crust layer was determined numerically based on the article descriptions of topsoil and cultivated soil in the archived calendar maps. The groundwater levels distribution was obtained from groundwater observation wells installed by the national and prefectural governments. Figure shows the distribution of the calendar maps used. The total number of calendar maps used in this study is in figure. The analysis of calendar maps in this study revealed the presence of crust layers with varying thickness. The thickness crust layer observed was 1.5 meter, indication that crust layer ranging from 0 to 1.5 meter are extensively distributed across the Saga plain. Concerted crust layers are seen at point A, B, C, D in figure. In particular, crust layers with a thickness of about 1 meter are concentrated at points C and D in figure. Figure shows the depositional distribution of two types of clay and the thickness distribution of the crust layer. The crust layers are distributed where the upper part of SEAGC formations are concentrated in the naturally landed area because the boundary line of the thickness distribution of the upper part of SEAGC formation in the boundary line of the naturally landed area. Therefore, the crust layers are concentrated in the naturally landed area. Figure shows the location of the national and prefecture observation wells. A total of 12 observation wells, 5 in the Saga area and 7 in the Shiroishi area, were used in the study. The overall trend was that groundwater levels was lower in the Shiroishi area than in the Saga area. In the Shiroishi area, groundwater levels become shallower than immediately after the compression of the Kasegawa Dam due to the influence of the large amount of groundwater extraction that continued until 2013. In the Saga Direct, on the other hand, there is no significant difference between the period immediately after the compression of the Kasegawa Dam, the period after the compression of the Kasegawa Dam, but the amount extracted groundwater has been decreasing year by year. This is thought to have caused the groundwater level to rise. The crust layers are distributed where the upper part of the SEAGC formation is deposited on the surface. Therefore, the crust layers are concentrated in the naturally landed area. With the compression of the Kasegawa Dam, the Shiroishi area is no longer dependent on groundwater for agricultural use, resulting in the significant decrease in the amount of groundwater extraction. Therefore, the groundwater level in the Shiroishi area increased significantly. The findings of this study are summarized as follows. Also, the above basic results on crust layer thickness and groundwater levels are obtained. The academic basics for using the crust layer depth to determine the ordinary water surface remains to be determined, and further research is essential. We believe that the system developed in this study can be fully utilized to study crust layers and groundwater levels in the future. Thank you for listening.
Okay, thank you very much, Ms. Kurishima. Let me open the floor for questions that you may have. Questions?
Okay, so maybe then there is any question? No? Okay, so thank you for your presentation. Just a clarification question. I'm not sure how can you get the thickness of the crust layer in your presentation. Can you explain a little bit more?
We'll ask for a translator.
クラスレイヤーの厚さによってもうちょっと詳しく教えてください。厚さ。
クラストレイヤーだいたい1メートルぐらいあるのが佐賀では通常です。
She said the crust layer is around 1 meter per area. So based on that, they're gonna make the wooden pile, the construction of wooden pile.
Like take the sample out, something like that, or?
サンプリングとかしたりしますか？
今研究の続きとしてやってる最中。
もう一回。
今研究の続きとしてこの研究の続きとしてサンプリングをしている最中です。
they are still under investigation. So she got some data from different area. The real problem is related to when they want to build in Sagalolon, it's really soft, so they have to put a wooden pipe. So when the wooden pipe come out of the groundwater level, it's exposed to O2. When it's exposed to O2, it's rotten. So they try to understand the real water level, the real level. Based on that, they're gonna make the construction. So they are still under investigation.
So, thank you, and thank you for your translation.
You're welcome.
So any other questions? Okay, I think we can proceed to the third and final presentation for this afternoon. The title of the paper is entitled, or the presentation is entitled, Verification of Piezo Drive Cone Data Against Standard Penetration and Cone Penetration Tests, a case study in Taiwan. And this will be presented by Yu Shuan Zhou. So, Dr. Yu Shuan Zhou is with the Department of Civil Engineering from the National Taiwan University.
Thank you for the introduction. Hi, good afternoon, everyone. My name is Yu Shuan Zhou, a postdoc researcher at National Taiwan University. It's my honor to be the last presenter of the last session in this conference. Okay, today I'd like to present our research. The topic is verification of IPDC data against CPT and SPT, a case study in Taiwan. So let me show the laser pointer, okay? First of all, what is IPDC? IPDC is Intelligent Piezo Drive Cone, a dynamic penetration device developed by OYO Corporation in Japan. It is designed based on the concept of SPT and CPT, and which is a ground investigation tool and used for evaluating soil liquefaction potential. Okay, the biggest feature of IPDC is that the pore pressure transducer and low cell are installed at the rod tip. And let's see a short video of operating IPDC. In this video, we can see there's a hammer is lifted up and dropped down automatically. Okay. What's the purpose of the installed pore pressure transducer and low cell? Pore pressure transducer is used to measuring the excess pore water pressure excited by each penetration. And the fines content can be estimated through empirical equation without sampling for physical property analysis. The low cell is used to measure the reaction force at the rod tip generated by falling hammer impact energy. And then we can use the rod tip reaction force and blow counts to obtain an energy corrected ND value, which is equivalent to SPT N60. And the raw data, the raw data of IPDC are recorded automatically by impact trickling sensor. So we obtain continuous data against steps from IPDC. Before operating IPDC, it is important to ensure that there's no backfill with concrete blocks, construction waste, or there's no underground structure or pipeline in the surface part of the soil. So the first step is to excavate a hole with 70 to 100 centimeter depth to exclude the obstacle at the borehole location. But this step is optional. In this study, we have confirmed that there's no backfill underground structure and pipeline at the testing area. So we decided to operate IPDC directly without excavation in advance. The second step is to set up IPDC device. Following this, rod tip with porous stone and is installed at the rod tip, and the first drill rod is positioned and erected to the ground, so that the subsequent drill rods are perpendicular to the surface. Then operating IPDC. And finally, after finishing test, a withdraw device is used to pull all the rods out of the ground, and then we restore the sites before we leave. The test site, Tianzhen Fishing Port in Kaohsiung, here, the Kaohsiung, was chosen to perform SPT, CPT, and IPDC, located in south of Taiwan here. And a multifunctional aquatic products distribution center is planned to be constructed. And here's the image of the sites. According to the overview of turnkey project, the wrapped foundation excavation depth is 1.5 meters. And according to the soil profile, the soil layer above 9.7 meters are very loose to loose sandy soil with clay soil. And they've done soil liquefaction analysis and found out that at the design earthquake, this site has medium to severe liquefaction severity. So these sites, applying ground improvement on this site is necessary. And then they adopted rapid impact compaction method, RIC. Okay, here's a short video of operating RIC. This slide shows the configuration of boreholes. The boreholes were all drilled to a depth of 12 meters. And this site has two pilot testing areas, A and B. The difference between area A and B is that area A has 9 relief wells to dissipate the excess pore water pressure excited by compaction effectively. And the borehole locations of SPT, CBT, and IPDC are indicated by circle, triangle, and plus signs respectively, and they are set diagonally. Like these 4 are SPT, these 4 are CPT, these four are IPDC. And the average distance of borehole is 270 centimeters. And A1, A2, B1, and B2 are the boreholes before RIC, and A3 and A4 are the boreholes after RIC. And here's come to the results. Here's the results of N value before RIC. The black dot data is the original ND value of IPDC. The blue dot data is the energy corrected ND value of IPDC. The red triangle data is the SPD N60. And the final, the green square data is the SPD N60 converted by CPT cone tip resistance. And we can see that from these results, the soil profile of area A1, A2, B1, and B2 are similar. And here's a weak soil layer between the depths of 3 to 6 meters. And we can see that the red dot here, the red dot, most of the SPT data points lie on the CPT and IPDC curves. And compared to the n value converted by CPT, the SPT N60 value is primarily located on the IPDC energy corrected ND curve. And then we compare the fines content obtained from the lab test with estimated fines content from IPDC. And here's the results. And we can see most of the SPT data points fit with IPDC data. And these are one of the boreholes of reports of SPT and CPT respectively. The left-hand side is SPT physical properties report, and the right-hand side is CPT report. Let's focus on the weak soil layer at the depths of 3 to 6 meters. The soil layer was classified as CL, and its fines content almost 100. And according to the CPT report, the soil behavior type at this range is sensitive fine grain. Let's see the result and value result after RIC. Area A3 and 4 are the results after RIC. And we can see that it is obvious, you see here, it is obvious that N value increased significantly above 3 meter depths. However, below 3 meter depths, there's no significant difference between before and after improvement. This indicates that the RIC methods cannot improve the soil layer with poor water permeability. And here is the fines content results after RIC. And finally, comes to conclusions. This part, comparison of SPT, CPT, and IPDC, and the effectiveness of RIC at the pilot testing area. Here's the summary of my presentation. And our conclusions are that IPDC can be another option of device used for ground investigation, and the data can be used to determine the vertical scale of fluctuation for spatial variation later on. Thank you for your attention.
Okay, thank you very much for your presentation. And so I open the floor for questions that you may have for the speaker. Questions? Yes.
Can you go back to
Yes.
page 12? Page 12.
12.
You can see in area A3, at a depth of 7 to 8 meters, the SPT N value is apparently larger. What is the possible reason?
You mean this red dot, SPT?
Yeah, you can see the red
Here?
triangle. It is apparently larger than other results.
Yes.
What's the possible reason?
Actually, this kind of situation is happened at right here and in here. Some of the results have the difference between each other. So I think there's a partial part of the ground difference between each other. Yes. I mean, I think it is not influenced by RIC. Thank you.
Okay. So, are there any other questions? Okay.
Thank you. My question is that you correlated the results from the SPT and also from the CPT results from far points of 270 meters. The proximity of that data or that points from 270 meters apart from CPT to SPT, do you think it is representative correlation for that value? Thank you.
You mean each borehole will affect each other, or?
You did a correlation between CPT and SPT for a 270 meter length or distance. Do you think it is conclusive that the correlation is reliable from that distance?
$2.7 meters. The distance between each borehole is 270 centimeters.
Okay,
Yes.
Thank you.
Yes. So sorry, I didn't present clearly.
Okay. I think we have run out of time, so I'd like to thank all of our speakers, and let's give our speakers one last round of applause. I'd also like to thank the audience for their participation with their questions, and we will close now this session on ground investigation. We will have a brief 15-minute coffee break, and we will then proceed with, after the coffee break, we will proceed with the closing.
ค่ะ สวัสดีค่ะ สวัสดีค่ะทุกท่าน We are about to begin our event closing ceremony in a few minutes. Please find your seat and make yourself comfortable. Okay. As you know, in every race, there is a finish line. In every sentence, there is always a period. And in every story, there is always a last chapter. So, ladies and gentlemen, we have come to the end of this wonderful conference. So, on this occasion, I would like to invite our beloved President, Professor Dr. Suthisak Soralam, to kindly deliver his closing remarks. Please give him a warm welcome.
Thank you very much. Finally, we came to the closing ceremony, and then I hope that during the past 2 days, you guys have a fruitful information, discussion, and then and also you enjoy the exhibition that show outside. First of all, as a duty, as a president, I like to conclude and summarize the information of the conference that we have here. Can you show the slide, please? We have the total number of 253 participants, not include the student that joined. The student is almost about like 100. So we have about like 353 participants from several kinds of government sector, sponsor, some of the student register and non-register about 100 as I already told you. Next, please. And we have the participant as a nationality, about 15 countries, quite a lot. Cambodia, China, Hong Kong, India, Indonesia, Japan, Kazakhstan, also have Kazakhstan here. I just went to Kazakhstan, by the way. Korea, Malaysia, Mexico, we have Mexico. Wow, we came a long way. Nepal, New Zealand, the Philippines, Singapore, Taiwan, Thailand, of course, United Kingdom, and then totally 253. Okay, next please. And we have sponsor exhibition booths outside. You can see we have 18 booths, exhibitor. And if also add the sponsor, which is not the exhibitor, we have about 27 sponsor. Okay, and then I talk with each sponsor, try to convince that for the next conference that we're going to hold in the Philippines, and they are all interested to go to Manila. Okay, all right. Finally, I'd like to thank a special thanks for our host, which is Thai Geotechnical Society, in which Professor Aragon is the chairman of the local organizing committee. Please give him a big applause. And of course, he's a representative of all the committee members that help in this event. I would like to also thank to the Engineering Institute of Thailand, which also send the staff to help. For example, our MC here is from EIT. Okay, please also give a big applause for EIT. And I also like to say thank words, okay, to Dr. Shin, which cannot join us today. Dr. Shin is the chairman of the SEAGC-AGSSEA, Association of Geotechnical Society in Southeast Asia. He couldn't come to our conference because of the family business, urgent family issue. But anyway, he been helping a lot in terms of setting up and then try to help in many ways. So please also give him a big applause. Okay, for the Southeast Asian Geotechnical Society, my presidency will be finished after the end of this conference. And the next chairman of our society will be Dr. Jeff Chow. So I would like that you guys, especially all the sponsor or the student, will support him, okay, in order to organize the next one, okay? And also he taking care the Southeast Asian Geotechnical Journal. He's the editor of the journal, okay? So please send the paper to the journal, okay? For the next conference, as in the last in the gala dinner, I already announced, but maybe some of you may not know. The next conference will be in the Philippines, in which I would like to thank Professor Mark Sako and then the committee or the committee member or the board of the Philippine Geotechnical Society to accept the invitation to be the next host. And I would like to take this opportunity to invite Professor Mark Sako to give a few words. And then, please.
Good afternoon. I'd like to thank, of course, congratulate Sutisak and the Thai Geotechnical Society on a very successful conference. And I'd also like to thank AGSSEA for choosing Manila, Philippines to be the next site for the next or the 22nd Southeast Asian Geotechnical Conference and the 5th AGSSEA conference. So the Philippine Society is the youngest society, I think, in the AGSSEA, and also the ISGM family. And we do consider this the honor to be awarded the opportunity to host the next conference. So I promise that my team will try our very best to be able to match the very high standards shown in this particular conference. And we hope to see you 3 years. And as we say in the Philippines, mabuhay. Thank you very much.
Thank you very much. That will be in 2026. 2026, and I'm also exciting to go to Manila because there's a lot of project over there. Underground train, underground subway, right? And also SkyTrain, some airport project, and also you said about the bridge, one of the longest bridge, 40-kilometer bridge. Think about that. Interesting, yeah? And also you also have typhoon anyway. Okay, I think that's all for the conference. I like to thank everybody here, and also some those already left. And I like to wish all you guys go back home safely. And then some of you may stay longer. Please enjoy Bangkok, enjoy Thailand. There's lots of things to do here. And you are at the location where is the city center. This is the real city center in Bangkok. Okay, you can go many ways and as you want. And shopping time is started now, right? Thank you very much, you guys. See you in the Philippines. Thank you.
Thank you, Professor Dr. Suthisak Saralam นะคะ Okay, this is a simple and beautiful word. Thank you so much, and we will look forward to see you again in the 22nd Southeast Asian Geotechnical Conference in Philippines. Goodbye. Thank you very much. ขอบคุณค่ะ